Ciao, Merovius.
Meeting is being recorded.
Thanks. And I was asked to introduce generics, which is a new feature coming in Go 1.18, which is being released soon. Like the first release candidate of 1.18 is already out, as far as I know. So in the next few weeks, we should get the full stable release of Go 1.18 with generics, the long-awaited feature. And when Anna asked me to introduce, to talk about generics, I decided that I don't want to just do the regular thing where I talk about map, reduce, and all of that stuff, because I thought everyone does that. That's boring. So instead, I'm going to talk about a specific use case I have in mind where I want to use generics at work. And I will try as much as I can. I will try to introduce all the features and all the concepts that are relevant based on this example. Generics is a pretty huge language feature. So this is a bit dense. And to be quite honest, the fact that I chose to first have you understand what I'm trying to do with this example is probably not the best decision. But I hope we can get through it, and I hope it's a bit more interesting than to see theoretical examples. So let's start with getting into what the current situation is of this example. What are we doing, and a little bit of what the problems of the current approach are. So we have a service, and we split the business logic of that service into many providers. So every provider, you can kind of think of it as an RPC handler. It takes some inputs, it does some calculations, it maybe calls into some other providers, and then it provides an output. And there might be one output, or there might be many. And the idea behind this abstraction is the people who write providers are very different people from the people who maintain the service as a whole. So this abstraction allows us to have people who are more qualified to talk about the business logic and write the business logic, implement providers, and we just give them an interface that they have to implement. The way this interface works is this provider interface. So every provider has an ID, which is basically just a string. It gives these request type and response type. It has these request type and response type methods, which return reflector types. And these are there so that in the server code, we can allocate new request messages when they come in and return them. And marshal them. And then we have a run. Every provider has a run method, which takes a context. It takes a publisher. A publisher is, I will talk about a publisher in a second. And it takes a request message. A message is just an interface that has JSON marshal and JSON unmarshal methods. And a publisher is basically the equivalent of an HTTP response writer. You call into it to publish your results, right? And the reason it's called publish is basically for historical reasons, because this uses pubs up. And then the provider package also gives providers two functions called call and stream. And these are used to call dependencies, to call other providers and get their responses back. So call just returns a single response message, and stream returns a response iterator, which can be used to iterate over multiple responses, right? So basically, this is really just an abstraction for RPCs, more or less. They don't necessarily have to be remote, we decide based on load and all of that, or that's at least the plan. But it's basically just an RPC abstraction, more or less, and the method to call is identified by this ID, right? An implementer of this provider would then look like this. And this is very, very dense. I tried to fit it all onto like one slide. So it's every provider is implemented in its own package. It has a global variable ID, and this is for static analysis because we want to have like call graphs and all of that, and also to like identify the actual function. It declares a request and response type, which are just structs or whatever. Like they could also be slices. It has a new function which just returns the provider, and then the provider is basically like the ID returns the ID, the request type returns like the request type. Like this is all boilerplate, right? And then the run method is the meat of the provider. And the run method, like the first thing it always does is it takes the request, it type asserts it because request is a message, it type asserts it to its specific request type so that it can actually unpack the fields. And then it does stuff with that. And then if it wants to call a dependency, like if it wants to call into another provider, it calls this call function, gives it the ID of the dependency with a request of the dependency. And then type asserts again the returned message to the right response type, and then does something with that. And then finally it publishes a response message, right? Like this is basically the boilerplate of what a provider looks like, right? Now the problems with this approach are kind of obvious. So for one, it's possible like call, stream, publish, all these functions and methods, like they all take like what are essentially like they take the message interface, but it's always possible to pass the wrong message to a provider, and then the provider like in a call, and then the data gets marshaled to JSON and unmarshaled into the wrong data type, and things go wrong. And we had that happen. There's also the problem, this is very visible here, is that like we always need to do these type assertions, and these type assertions always need separate variables. Whenever we do a call, we need a separate variable to do the type assertion. And like like this is really inconvenient, especially if we have like multiple responses and all of that. The responses are often pointers, often slices. But to make the logic in the server simpler, we always assume that the request and response times are pointers, right? Because we always call like reflect.new, and this is always like this means that the provider actually has to publish pointers to slices, which is very unidiomatic to do in Go, but we have to do that this way. And it happened fairly frequently that we run into bugs where we forgot that or stuff like that. And then tests might not have caught that, and things went wrong that way because like we couldn't unmarshal it because the types weren't matching. And then also it's just like there's a lot of boilerplate here, right? And we might like we really want to get rid of that, right? So that's kind of the state where we're in. And next, like, how do we intend to solve this using generics? So this is the first part where I would like to ask, is this reasonably clear, like what we are doing and what the problems are? Let me actually try to figure out like if a yes or no by one of the other moderators would also help. But I think this looks great. Everyone is giving, yeah, great. So how do generics solve our problems? How do they solve all our problems? So the thing Go 118 gives us is type parameters. And type parameters means we can add to any function and any type, we can add type parameters. This is what is happening here. So where previously our publisher interface was just an interface that had a publish method, which took a method. Now we parameterize it with this syntax to say every publisher also has an associated response type. This is any type, and publish must be called with this response type. And before we can use a publisher, we have to instantiate it. We will look at that in literally a second. And then also the provider, like the provider gets parameterized with request and response types. And we can use these in the run method to say, well, the publisher we pass is actually a publisher for this specific response type that is taken from this parameter, and this specific request type, which is taken from this type parameter, right? So instead of saying just it's any message, the provider interface now gets annotated with the specific request and response types which are used, and we just pass them on directly. Similarly, like we can see how to use that with functions. Functions just add the type parameters after the name, like types also add the type parameters after the name. And now the call function can just take a request, return a response, and then when it's instantiated, we will see that in a second how it's actually used. We can see how this actually makes it type safe and solves most of our problems. Similar to stream, we parameterize the iterator interface to actually give us specific response types, and we no longer have to type assert on messages, right? So point one, we can add type parameters to any type declaration and any function declaration, which, like, if you know C++, if you know Rust, if you know Java, like, you know those, right? But now we get them in Go, and this is the syntax. So also one thing we can see directly is the request type and the response type methods are now gone from the provider interface. We no longer need them. We can get rid of reflect in this case, because the provider, just by virtue of its type, already tells us what its request and response types are. And now the same implementation we had before would now look like this. We still have the ID. We still have request and response structs. But now the new function doesn't just provide return a provider.provider, but it returns a provider.provider instantiated. This is like, we call this instantiation. So this is a generic type, and we instantiate it with request and response pointers, which means this is now a specific type for these specific requests and responses. And then to implement this interface, we just use the corresponding types in the run method, in order methods where it's relevant, right? And so we can see here the run method now takes a provider for a publisher, for a response pointer, and it takes a request pointer directly. And then we no longer need to type assert a request, because this is now just a pointer to request and no longer a message. So we can just use that directly, so that just goes away. And when we call the provider, we instantiate it again with the request and response types of our dependency. And now the compiler will actually tell us, if we would use a different type here, the compiler would actually tell us this is not the right type, because you instantiated it with deb.request, but you passed me a not.request or whatever, or an integer or a string or whatever, or not a pointer. Like, the compiler will just complain at that point. So we get type checking of arguments that we pass to call, which is great. And then also the same for publish, right? So again, this is, so basically, type parameters, instantiations. Is this roughly clear, right? The syntax for type parameters is you add the parameters after the name, and instantiation is you use the generic name, and then you use brackets to add the actual type parameters that you want to, the type arguments is what we say, right? Type, like, just a nomenclature. I don't know how I will actually keep to that, but the nomenclature is, these are type parameters, these are type arguments. Like, what you pass is an argument, what you take is a parameter, more or less. Okay, next step, type inference. Writing this out every time is kind of tedious, right? Having to always instantiate it explicitly, that's kind of tedious. So the compiler allows us to often omit type arguments. So for example, instead of writing pub.publish bracket pointer response bracket response, we can also just write pub.publish and pass the response directly. And the compiler can look at that and see, oh, you're passing it a response pointer, so I already know that this has to be a response instantiation, right? But one limitation of that is this actually only works for function calls. Yeah, not for function calls. This only works for arguments passed to a function call. So for example, we can't do this with the call function, because while the call function mentions the request type in its argument, the response type is not mentioned in the argument. So the compiler actually, like, it only looks at the call expression. And if it can't infer the type from the call expression, which only includes the arguments and not the responses, it just can't do type inference, which is why the call function we actually still have to instantiate explicitly. But that's also like a decision. Like, we might make type inference more powerful in the future. But for now, the decision is kind of, we want type inference to be as simple as possible and as understandable as possible, so that when things go wrong, you always know why. And if things go wrong, or if the compiler can't infer types, you can always just write it down. And so there's always a kind of shortcut to a breakout, a fix, a workaround to fix a missing type inference, right? But this is something that is very useful to keep in mind, because it's very useful if you write generic code to try to write it in a way that actually puts all the generic type parameters into the arguments in some way, because that will allow us to omit type arguments, which makes code much more readable, right? So one problem with where we are at right now is call isn't actually safe. So to illustrate that, we instantiate call with the request and response types, and then once we did that, the compiler will complain if we passed the wrong request, and the compiler will actually give us the right type for the response back. But the compiler will not prevent us from using the wrong request or response types in these situations, right? Like if I were to write int in here, the compiler would be totally fine for me to pass an int in here, even though the provider that I'm calling doesn't know what to do with an int. It only knows what to do with a dep.request. So even though we gain like some measure of safety, we don't get a lot of safety. But there is a little trick that we can use. This is what I just said, is we can try to design our APIs so that we always mention the type parameters in the argument. And I want to warn you, I'm not entirely sure whether the community will like us doing this or not, like whether this will be a pattern that the community will like. But I think for this case, it's actually clever and fine, which is we can add the request and response type parameters to the ID type, even though it's just a string, even though it doesn't use it. But by doing that, we make it so that both request and response appear in the arguments to call and to stream, right? Because now response is part of an argument, and when we call it, the compiler can now just infer request and response from the ID that we pass here. But it also means the compiler can actually check, right? Because if we now pass the wrong type, if we instantiate provider.call with the wrong type, it will complain, because it will see that the ID has the type, is parameterized with dep.request and dep.response, but that we instantiate call with wrong. And so it will actually say, this is a mismatch, this doesn't work. Right, Sasha, there is a question. Because this is a weird thing, I want to be sure to.
Yes, there's a question, but maybe a strange one, you tell me. If we have a type definition like type ID string, and we have an interface which is a generic interface, and we have an instance of a type implementing that interface with the type ID, then essentially as a type ID is a string, can we cast down or type assert this to an interface of string? Which would then maybe mean that we lose the request response any.
Can you? I'm not sure I understand the question. So what you're saying is, let's say we have a type. I don't know if that. I don't know. Can you repeat it?
To make it simple, leave out the type, the request response any, and just type ID string.
Yeah.
And then if we have a call or a type which is generic, like type publisher ID interface, then there's an instance. We make a type which is, and then we can we cast it to type string. So like I could assign the ID to a string in normal code. So can I change type implementation and interface type to something which is a string, but which was created by using the ID type?
I'm sorry, I'm really not sure if I understand the question. Do you mind, like,
Sorry
can you
to
like
interject here for 1 second. If you show something in the browser, can you make the font size a bit larger in case you show something?
Yeah, I can, like this I can do.
Exactly. Thank you.
But I'm not sure I understand. Like, I don't understand. I'm not sure I understand Sasha's question well enough to even do that. Sasha, can you maybe give a playground example or something? And then maybe we can get back to that, come back to that question. Is your question just, can you do this better? Because if your question is, can you do that better? Then the answer is yes, maybe, I don't know. Let's talk about that later. I don't think
we can talk about it later, but it wasn't about better. But if I have a type provider, any interface which I then implement for the type ID, which is defined as type ID string.
Yeah.
And I have then that program running, can I then later cast it to something which is of type provider string interface? Because ID would not, I could type assert ID as string.
Yeah.
Can I type assert generic?
No, you can't type assert. You can convert it to string, but you can't type assert it to string because
yeah.
ID
Can I convert?
String.
Can I convert the generic interface implemented struct to something downwards? So can I convert from struct ID to struct string? I'm not sure why I would do it, but it's just something which came to my mind.
Like, if I understand your question, I think the answer is probably yes. But let's try to talk about that later.
I think it's a bit too complex, and we should skip it because it's probably better in writing.
Yeah, right. And I think, like, for the record, these specific 3 slides they are a strange trick that I came up with. I'm not quite sure whether you, like, if that is what you don't understand, then just skip, like, forget about it. That's fine. The rest of the talk is far more important, right? So I would like to continue. Right. But with this ID thing, if we just write this, we actually get full type checking. Like, this actually means the dependency, because the dependency provider declares for its ID what its specific request and response types are. When we pass it to call, the compiler will actually check both that the request is correct and it will make sure that the response type is the correct thing. So string string ID high. So Bene just posted a question. The question is, if this is true, let me type this here for the recording. String it reg resp high string it, oops, it's high. And so one, no, because this is not parameterized, but if you would put like int float 64 here, then yes. Then you can convert both of these to string and it will be the same, exactly the same. So if that is the question, I hope now the question is actually clear. Like this would work actually. Like this code would work. Which for our purposes, like you can always break, but like this is fine. The whole point is just that if you write the natural code, if you write this code, which is the natural code to write, you get full type checking. That is kind of the idea here. Like, yes, if you write non-obvious code, if you convert things back and forth and stuff, we actually did consider at some point to make, like, if I was really, really, really serious about preventing all of that, I would make ID a struct type with unexported fields, and I considered jumping through a couple more hoops to make it harder to break, but I decided that I don't mistrust my coworkers that much. I just want to make sure that the obvious code works and the obvious code is type checked. But yes, I could always make it harder. Like I had some ideas to make it harder, but I decided that it's not worth it. Anyway, right. So next. So far, all our type parameters were always like any, like we always had these any type. But originally, we said that requests and responses should always be messages because they should always implement JSON marshalling. And the way to fix that is we can actually give constraints. So we can actually say, instead of using any, we can actually use an interface type as the meta type of a type parameter. So where normally you would in a normal parameter list, you would have the type here. So here now we have the meta type, the constraint. And so message is just a JSON marshaller, JSON unmarshaller. And by this we say request and response actually have to implement the message type, which means that every time we instantiate a provider or whatever with a specific request and response type, the compiler will actually check that the requests and responses implement the message interface. And every time we use a provider and call a method, we use the request and response in a generic function. For example, if we use the call function, like the call function actually has to call the JSON marshal and unmarshal functions, right? To actually marshal it into binary and then into JSON and then unmarshal it again, the response. It is now allowed to do that because we have specified that request and response actually do implement the message interface, right? So this is both how a generic function can call a method on a type parameter and how a instantiation is checked that it actually that the type arguments we pass actually do have these implement these interfaces. So for example, we can't actually instantiate provider.id with int and string because int and string do not satisfy provider.message because they don't have the right things, the right methods, right? And now, as I said, like call can now actually call the method, the method, which like it can't call the foo method because message does not contain a foo method, right? So it can call marshal JSON, it can't call anything else on the type parameter because the compiler says, well, you just told me that it's a message, right? But if it's a message, it doesn't need to have a foo message. Method, sorry. And the any we saw before, like all the any we saw in the type parameters, is just a new pre-declared alias, a type alias for empty interface, right? So any literally means any type. Yeah, that's actually true. Sorry, there was a phase where there was an asterisk there, but this asterisk went away in the meantime. Sorry. Yeah, any is just an alias for empty interface. It's literally that. And so also, if you look at library code, at documentation for Go 118, you will actually see that the standard library now uses any wherever it used to use empty interface. Like they just did a global string replace where like empty interface was replaced by any. Excuse me. Right? So this is how generic functions can actually say the type I take is actually, it has to do more than just be any type. It actually has to do things like it might have a less function or whatever, a less method or whatever. Sorry. Questions for constraints so far? How constraints work? 3, 2, 1, great. Interfaces only give us methods, but sometimes we also might want to use operators in a generic function. For example, we might want to write a generic maximum function that we can put in, like, instantiate with ints or floats, which will use the less than or greater than operator. And the way the Go design accomplishes that by introducing something called typesets, where basically it introduces, it allows you to in an interface write what they call a type element. And the type element is either a type, then it says this is the set that only contains t. It can be tilde t, which means it's any type with underlying type t. If you don't underline what the underlying type is, that's just the underlying type is the type that is used in the type declaration. So for example, our type ID string, the underlying type of ID is string. And then as pipe t is the union of the sets s and t. And so by using unions and underlying type and type, and then by putting lines under each other, if we put in an interface lines under each other, we get the intersection of the type sets. We can build more or less arbitrary type sets. And then if the generic function can use an operator if all the types in the type set of its constraint support this operator. I will show an example in a second, right? So for example, we can now declare an interface that is any integer type by just explicitly saying, well, it either has underlying type int, or it has underlying type int 8, or underlying type int 16, and so on and so on and so on. And this covers all integer types, like both all the built-in types. It also covers, for example, time.duration, which has underlying type int 64. So this covers every integer type. Or for example, we can define an interface for underlying type string or underlying type byte, which allows anything you can do with both a string or a byte, because both are kind of sort of like collections of bytes, like sequences of bytes. So we can use this constraint to say, well, we basically everything the bytes package does and everything the strings package does can now be combined more or less into one package, which would work on the byte sequence, right? And one example of how to use this is, for example, say we have a concatenation function which takes a bunch of byte sequences, so strings or bytes. Basically, we want to unify strings.concat and bytes.concat. It just declares, so this has the constraint byte sequence. We take an arbitrary number of those t's and we return a t. And then this is the important piece is we can't use out plus equals piece, like string allows to concatenate using plus, but byte slices don't. So we can't actually use this piece of code, this line of code. This doesn't actually work because not all types in byteseq support the plus operator. But both strings and byte slices can be appended to byte slices. This is a special case in the append function, which says that the second argument is allowed to be both a string or a byte slice. So this is actually allowed. And so by just saying like append to out all the pieces, and then we have to cast it back to out to t, because we have to return a t, right? But this is allowed again because both byte slices, because the byte out, which is a byte slice, can be converted both to byte slice byte and to string and to everything that has underlying type, either of those. So again, all the things in the type set byteseq support conversion to t. Therefore, we can convert to t, right? Is this clear? How to use typesets to use operators and operations. The one thing to say I want to be clear on is that the actual spec on this, last time I checked, which was like last week, was still a bit wonky, and still not entirely, it's not entirely certain how we will write all of this down so that it works, because it turns out this is more complicated than one would think, and I spent a lot of time forcing people to make this more complicated so that we can prevent some bad things happening. But the actual details of how this actually works in the spec is, in my opinion, incredibly complicated. But I think in actual usage, this will be fine. This will usually just work. But just saying that this is a bit up in the air still, but good enough. Right. Yeah, instantiation when we have typesets, typesets is allowed if the type argument is in the typeset of the constraint, obviously, right? Obviously we can instantiate our concat function with anything that has underlying type string or underlying type byte slice, but not with integers, because bytesec is only string or byte slice. As a special case, it's also possible to use type elements directly in constraints. So you don't always have to wrap them in an interface. If all you want to do is say this type parameter must have underlying type something, or must be one type or another, you can write that directly in. For example, this join function, it just says s must have underlying type string, and this just works. This is a nice quality of life convenience thing that they introduced. And then this joint is implemented using things. This is not important how this these details. But the reason this is interesting is this allows us, for example, to use the join function with things which are not just strings. For example, we might have a package which uses file system paths, and it might declare a path as just a string. Yes, correct. That's one of the nice things, is that you can't mix strings and byte slices in one call. Or maybe it's not the nice thing, but anyway. Say you have a package which declares file system paths. It can just declare path as a string. It declares a separator, and then you can actually use this join function if it's declared like this. And this join function, when you will be inferred as instantiated with path, because we path a path argument, and it returns this instantiation returns a path. So the return types match, the argument types match, and so we don't have to convert our arguments back and forth from string, but we can just use it and say because a path is just a underlying type string, we can just use that directly, right? So this is, again, convenience. Cool. So that in order for us not to constantly write down these typesets, the intent is that most programmers will almost never have to use explicitly write down typesets. If you just want to write a function which uses an operator, you can use the constraints package, which is in golang.org/x/constraints. Asterisk, you might, if you followed the development, you might remember this actually being in the standard library, but it was moved out of the standard library for basically based out of conservatism. We basically don't want to change the standard library yet. But the package exists, and it basically the intent is that it will provide most of the constraint typesets that you might want to use. And then you can just embed constraints.integer in your constraint and use constraint.integer, and don't have to explicitly write out these long lists. Right. All of this is theoretically. Oh, there's one very specific thing, which is comparability. Comparability is special in Go because you can't explicitly list all types which are comparable, because Go allows you to compare, like comparability means in Go means specifically comparison using equal and unequal, and it's not the same as ordered. You can't write a list of all types which are comparable, because Go allows you, whenever you have a comparable type and you have an array with that element type, it allows you to compare these arrays. So there are an infinite number of types which are comparable. The same if you have a struct which only has comparable fields, and it also becomes comparable, right? So comparable wouldn't work via this type set approach, this explicit union element list, which is why we introduced a specific pre-declared interface called comparable, which is done using compiler magic to just say this is any comparable type, right? Specifically, it excludes specifically functions, slices, and maps, and again, one asterisk, interface types. Even though interface types in the language are comparable, like you can compare to io.readers, it was deemed confusing to have interfaces implement comparable, because it means that you can have a function which says I need comparison to work. You can instantiate that using an interface type, like using any, and then the actual comparison might panic at runtime. So it was decided that it was safer to just say interface types don't implement comparable, so that we prevent this panic. And then again, we are being conservative for now. We will decide for Go 1.19 or the future how we want to do this. So let me actually write that just to make clear what I mean. If I like write, excuse me, my let me finish this slide. The main reason comparable will probably be needed is for use in maps. Like the map key type in Go must be comparable. So being hashable and being comparable in Go is actually the same thing. And so the generics design actually enforces that. Like if you use a type parameter as a key type for a map, the compiler will complain if T is not comparable and not declared as comparable. And this will probably be the most important use case for comparable. There are other use cases, but this will probably be one of the more important ones. So with that in mind, for example, if we take like we can write if we say T is comparable, we could write a set as a map T to empty struct. But if we do that, we can't actually instantiate it using, for example, any empty interface, because the compiler will tell us any does not implement comparable, right? Even though I can say, if I can declare two interfaces, A and B, and then I can write this. Like this works fine. The compiler still doesn't allow me to actually. Can I make this smaller? Apparently not, because I'm not hitting the right thing. The compiler will actually prevent us from instantiating set with any, even though we can compare interfaces. They don't count as comparable for the purpose of this, because again, it was like this. People did this, and then they said like as func equals struct, and then they panicked because they added a non-comparable value to their set. And they complained that it's confusing that I said all my things must be comparable, but I can still instantiate it with something that then panics at runtime, right? This is why comparable isn't implemented by interface types. Great. This is just a bit of an asterisk. There are a couple issues discussing this. The latest one is the one that I mentioned here. There are several ways we might solve this in the future. One of the things that is suggested right now is to make comparable a regular interface type. That you then can only store things in which are comparable. This would then allow you to embed comparable in interfaces and use make like comparable readers, for example, or comparable reflector types. And these types that embed comparable, you could then actually use to satisfy a comparable interface. This is one approach that we might take to fix this. I also have opinions, but if you are interested in the details, you can look at the issue. Right. All of this is kind of theoretical. Back to the example, but any more questions? Great. I've been talking for far too long already, but I think this is kind of the last thing that's happening now. One thing that is super confusing and super hard about this generics design, which I still want to talk about because I think people will encounter it, is there are some confusing situations around pointer methods. Our message interface so far just said it's a marshaller and an unmarshaller, right? And if we implement call, we might try to do this. Like call is parameterized by request and response. It takes a request, it returns a response. So far, so good. We marshal the request. We call a marshal JSON on that. We send the bytes over the network. We get a response back. We call response.unmarshal JSON with the response bytes. And then we return the response, right? This seems reasonable code, and it seems to do what we want. The problem is, if we actually try to use this, we will run into a trouble, right? Because our request and response types will probably be used as pointers, and more specifically, the unmarshal JSON function only works if it takes a pointer, because the unmarshal JSON function is a method is expected to modify its receiver based on the JSON data that it gets, right? So if we like define a request and a response type and we implement it for our interface, we actually get a problem, because if we instantiate a call just with the non-pointer types, this will be a compiler error, right? Because the compiler will tell us, well, the request and response type don't actually implement message. It's only the pointer that implements it, right? But if we instantiate it with the pointer types, on the other hand, our call function, as we implemented it, will actually panic, because the response is the zero value of the response type. And so if the response type is, if resp is pointer to request, then the zero value will be a null pointer. So we actually call unmarshal JSON on a null pointer here, and this will panic, right? So this function looks reasonable, but we can't actually call it reasonably, right? It just doesn't work, and this is a problem. The solution to this looks complicated, and it is a bit complicated, but I promise you it's understandable. What we basically want to do is we want to say we don't know, like we have to figure out what to write here, like how to define our constraints. But what we want to say is we actually call the marshal and unmarshal functions on pointers of request and response. But we still want to take the normal request and return the normal response type. And so what we want our constraints to do is to basically say we want request and response both to be any type, and the pointer to those have to actually implement the request and response interfaces, right? And so the way we do this is this. And again, I promise it looks complicated, but it's understandable. So first, our message interface, we parameterize it with a type T. And we say that the message actually doesn't just have to implement JSON marshaller and JSON unmarshaller. It also has to actually have the type pointer T. So we actually use type elements here, type sets here, to specifically say what the concrete type of the message interface needs to be. And it needs to be a pointer to T, where T is the type parameter, right? And then to call, we pass both the normal request and response types, and we pass two types, recp and resp, which are, these are the things that actually implement the message interface. And we say the message interface is parameterized by the plain types. So what we're saying is request P must implement message of request. So it must have type pointer to request to rec, and it must have these methods. So rec can be any type, but rec-p must be a pointer to rec that implements message, right? And if we do this, we actually can say we take the address of rec, like we still take the normal rec type as an argument. We still return a normal resp, but we can then take the address. We can convert it to rec-p. We have to do this specifically because the compiler doesn't know the association between address of rec and rec-p yet. This is something that might be addressed in the future, but we have to do this conversion manually for now. And then rec-p, the compiler knows actually implements the message interface. So we actually can call marshal JSON and unmarshal JSON. And like we know this is not nil. Great, right? So this actually allows us to implement call, and then we can just instantiate it. And we have to pass. Now we have to actually pass request response pointer to request pointer to response to because we had added these new type parameters. But then we can actually call it with a request and we get a response back, and that's great. It turns out this is super inconvenient to use, but in usage we can always whenever we use this trick, we can always omit these parameters, these type parameters. This is called constraint type inference, at least in the design doc, which means the compiler actually sees that request and response, what request and responses are, what rec and resp are, and infers from that what rec-p and resp-p must be. Well, they must obviously be pointer to request and pointer to response. And so we actually don't have to specifically mention them. What's more, because of our ID trick, if we actually do the entire shebang, we can even leave out both of these. So the reason I mention this is if you start using generics, A, you might sometimes have to write code like this, but B, sometimes you might have to use code like this. And then you might stumble over a message signature, a function signature, which actually looks like this. And in that case, you should understand that what's happening here is these types are there to circumvent this specific issue with pointer types, but you usually don't have to specify them because the compiler should generally be able to infer them. Again, always try to design your APIs so that type inference works. And as a user, always try to just not mention types until the compiler tells you that it can't infer them. Because obviously this code is much more readable than this code. But unfortunately, this is unreadable, but we can't get around it. Is what I'm saying, right? Questions about this specific concept? Great. Sorry, I have a bit of a sore throat, which is why I'm drinking a lot. Right. Last thing, second to last thing, there are a couple of library changes happening. One, we got 3 new packages. All of them were originally proposed for the standard library, but now moved to golang.org/x/exp because there were some discussions about what the right APIs were, and we wanted to just be conservative with that. So we put them in a separate repository from the standard library, so we are not bound to APIs that we later can't break. But you can use them; they work. Which is constraints, which I already talked about. Maps, which just gives functions for maps of any type, like give me all the keys, give me all the values. Map a map, like take a map and a function, and then map all the values or map all the keys. Slices, same thing, just with slices. And then also an obvious library change. All the Go sub packages have been updated to actually they got a lot of new API surface to deal with type parameter for tooling, right? But apart from this, as far as I know, the standard library basically does not use generics at all for now. It was pretty much decided to just hold off on any changes about that, so that we don't get locked into an API that we later don't want to support, because there is still a caveat in the release docs that there might still be cases where we have to change things, and then also there are a lot of open discussions about how to change APIs. But, the standard library has to be incredibly stable, has to be incredibly careful about the changes it does. And this is why basically the standard library doesn't take advantage of generics yet. All of this is in Exp. And then hopefully, A, we will learn there, and B, third parties will learn, and the ecosystem as a whole will learn, and that will tell us what is safe and good to put into the standard library and like what best practices are for that. Right. Last, I wanted to talk a little bit about limitations of the generics design, because there are questions that always come up when you talk about generics in Go. One of them is, this is probably the most frequently mentioned one. No, this is actually the second one. Is the most frequently mentioned one, even though this is, in my opinion, the more important one. There is no way to use generic functions or types uninstantiated. Right? Like you can write a generic function sort, but then you can't refer to sort. You can't just store sort, the generic function sort that works on any type, in a variable and pass that around. You have to always fully instantiate it before you can use it as a value. So basically, generics have absolutely no runtime component, right? Their name is reflected in the reflect package. If you have an instantiated type, like the reflect package has to know how to print that name, but there is no generic function that you can pass around. The types and values that you pass around will always be concrete types. And the reason for that is there was a famous blog post by Russ Cox a long time ago about the generic dilemma, and he posed a question that basically there are three ways to implement generics. All three of them are bad in some way. So that's why we are not adding generics to Go yet, because we want to find a way around this dilemma first. And the way they found to get around this dilemma is the generics design is very carefully designed so as to not prescribe any of these implementation strategies. We want all three implementation strategies to work. But this design would actually require a boxing implementation, or like a specific like runtime code generation or something. Like you couldn't, you would have to choose specific implementation strategies to make this work, because the place where the sort function is defined and the place where the sort function that you stored in a variable is used might be very far apart. The compiler might not have any way to know that they are related at all, because like maybe it has to solve the halting problem to do that or whatever. So this is why the decision was made. No, every function, every type has to be fully instantiated before you can use it. A related problem is that type methods can't get extra type parameters, and this is the most frequently brought up thing. For example, if you come from other languages, you might be used to the concept of a functor. For example, if we have a set type, we might want to write a map method, right? A map method that has an extra b type, and it takes a function from A to B, and it just maps the set by applying the function A to all elements and returns a new set B. This doesn't work in Go. Like you can't write a method that takes extra method parameters. You have to write a function instead. You have to write func map and then take the receiver as an extra argument. The reason for that is Go allows interface type assertions, meaning you can actually, like as an example, if we have a type X, we add a method f, which would be one such generic method, right? You could then write a type assertion whether the value X has a method f which takes an int. And theoretically, this type assertion would be true, right? Because it has a method f that takes any type. But the place where this type assertion happens might be very, very far away from the place where this definition happens. So again, doing this would kind of require the compiler to, like the implementation to choose a specific strategy to support this kind of runtime type generation or method generation, or it would have to box things. And we don't want to do that. Alternatively, we could just forbid type assertion. We could just say, well, as far as type assertions for methods are concerned, like these methods, like these types don't have these methods, but that seems strange, like giving them the methods, but then having type assertions on them fail seems a very, very strange Go thing, because like currently when it has a method, it has the method, right? Notice that this doesn't actually mention generics at all, right? Like it actually has the method. We could also say these methods don't actually are used for interface implementation at all, right? You can write the methods, you can type assert them, but like they are never used for interface satisfaction, and therefore the type assertion always fails. And you can also never use them to implement an interface. But then why make it a method in the first place, right? Because methods are basically only used for, like, that's their main semantic use, is they can be used to implement interfaces. And so basically the choice for now is you just can't do this, right? Which also means there's no monad in Go, there's no functor in Go. Like some abstractions people want to write, they just, like, you just can't write in Go. There are a couple other, like, more minor limitations. One of them is type parameters cannot be embedded. So you can't use an anonymous field of a type parameter type in a struct. The reason for that has to do with resolving names based on, like, resolving struct field names of promoted parameter types if you have like multiple embedded types. Like there are some complications there. Maybe we will never resolve this. Maybe we will. But again, this allows some things. Like, for example, I wrote a blog post at some point about something we could do about context. This just doesn't work now with the design as it is now, as it has changed in the meantime, because it relied heavily on type embedding. There's this limitation: a union element with more than one term may not contain an interface type with a non-empty method set. This is my fault, this limitation. It turns out if you allow this, you get into very heavy trouble with actually determining if the method call is correct, because that requires, like, this might actually be NP complete in practice, which we don't want, because we don't want to have to implement the SAT solver in our, like, Go type check or whatever. In practice, this is not a huge restriction, because you can always restructure your interfaces, and the natural way to write them will always be like work, hopefully. And then there are a couple of, like, minor limitations that are more like, we didn't get around to do this yet. Great. And that's it. So I already saw there's one question: are these slides available somewhere? Not yet, but they will be. I will upload them and link them on the meetup page, and also tweet about them or whatever. And then, like, other questions, I open the floor.
From my side, not really a question, more a remark. I think your ID trick is a bit like the var underscore equals to force the compiler to tell you about types you got wrong. Not quite the same.
Yeah, but I think it's similar. I think there's, like, I think type theorists, like functional programmers, know about something called phantom types, and I think that's basically what I'm doing here. But yeah, it's I think it's neat, to be honest. Like, I am really proud of that.
Yeah, I like it too. It's quite cool.
I think some people will object to that. But I think it solves the specific problems we were having, and it works really fine. And I think it does exactly what I want. Like, the result will be exactly what I want. So I'm yeah. Great. I don't see any questions. So.
Okay, so if there are no more specific questions left, then let me just say thank you very much. That was quite cool, and I'm really eager to dig deep into 118 as soon as it's there. But this is really great, and I also learned some new things. Neat.